we have discovered the first stars of the universe. Telescope observation catches is light from this distant object. And it's easier to think of how you can just have a gas cloud that has no heavy elements that just came right out of the Big Bang.
For decades, the universe's first stars have been a mystery, hidden in the cosmic dark ages. Now, the James Webb Space Telescope may have finally found them. This discovery could upend everything we thought we knew about the Big Bang, revealing how the earliest light ignited and how the first cosmic structures formed. The eternal darkness before dawn. In November 2025, astronomers made a discovery that sent shockwaves through the scientific community. The James Webb Space Telescope captured something that shouldn't exist, a tiny galaxy called LAP-1b, containing stars so ancient and so chemically pure that they might be the very first stars ever born in our universe. For 60 years, scientists predicted these population 3 stars existed. They searched, they theorized, they built the most expensive telescope in human history specifically to find them. And now, they might finally have proof. This discovery could rewrite everything we know about how the universe began. But before we explain why, you need to understand what the cosmos looked like before any star had ever ignited, a time so dark, so empty that astronomers gave it a haunting name. Imagine absolute darkness, not nighttime darkness, true emptiness. For the first few 100 million years after the Big Bang, that's exactly what the universe was. No stars, no galaxies, nothing but an endless sea of hydrogen and helium gas drifting through infinite black. Scientists call this era the Cosmic Dark Ages. And here's why it matters. During this period, the universe faced a paradox that seemed impossible to solve. To form a star, gas needs to collapse under gravity. But to collapse efficiently, gas needs to cool down. And to cool down, it needs heavy elements, metals, that can radiate heat away. The problem? There were no metals yet. They only get forged inside stars. It's a cosmic chicken and egg problem that baffled physicists for decades. So how did the first stars ever form? The answer shocked astronomers when they figured it out. Without metals to help, the first stars had to form differently. Massive clouds of primordial gas, millions of times the mass of our Sun, slowly contracted over millions of years. The process was brutally inefficient. Tiny fluctuations in density, remnants from the Big Bang itself, provided the initial seeds. Dark matter helped too, its invisible gravity pulling gas into clumps that would eventually become dense enough to ignite. But eventually, somewhere in that dark void, enough gas collapsed to ignite the first nuclear fusion reaction in cosmic history. And when that first star turned on, it didn't flicker to life gently. It exploded into existence with a fury we can barely comprehend. These weren't stars like our Sun, they were monsters, 100 times more massive, burning millions of times brighter, and destined to die young in spectacular explosions. The lifespan of these stellar giants was shockingly brief. While our Sun will burn for 10 billion years, population 3 stars exhausted their fuel in just a few million years, a cosmic eye blink. Then they detonated, scattering the first heavy elements across the universe and setting the stage for everything that followed. But here's the twist. Despite 60 years of searching, no one had ever actually seen one. They existed only in equations and computer simulations. Their light should still be traveling toward us from billions of years ago, but finding that light required technology that didn't exist. Until now, the telescope built to find the impossible. Finding population 3 stars wasn't just difficult. Many thought it was impossible. These stars burned out billions of years ago. Their light has been traveling across the universe ever since, stretched and dimmed by cosmic expansion until it became nearly invisible. The stretching is key. When the universe expands, it doesn't just push galaxies apart, it stretches the light traveling between them. Light that started as visible or ultraviolet radiation gets pulled into longer wavelengths. After 13 billion years of stretching, That light becomes infrared, heat radiation invisible to human eyes and most telescopes. To detect it, we needed something unprecedented. Enter the James Webb Space Telescope, a $20 billion gamble that took 3 decades to build. Why so expensive? Because catching ancient starlight requires catching infrared radiation, heat signatures so faint they're measured in single photons. JWST's mirror spans 6.5 meters, nearly 3 times larger than Hubble's. Its 18 hexagonal gold-plated segments collect light with extraordinary precision. But size alone wasn't enough. The telescope also needed to be cold. Impossibly cold. Here's the problem. Infrared is heat radiation. If your telescope is warm, it glows in infrared, drowning out the faint signals you're trying to detect. It's like trying to photograph a firefly while standing next to a bonfire. JWST's 5-layer sunshield keeps the instruments at negative 233 degrees Celsius, colder than any natural environment in our solar system. When JWST launched on Christmas Day 2021, astronomers held their breath. The deployment involved 344 single point of failure mechanisms. If just one failed, the entire mission was dead. Engineers couldn't fix anything. The telescope was headed to a point 1.5 million kilometers from Earth, 4 times farther than the Moon. But somehow, impossibly, every single mechanism worked. The mirror unfolded. The sunshield deployed. The instruments cooled down and powered up. The telescope's first deep field image, released in July 2022, stunned the world. Thousands of galaxies appeared in a patch of sky you could cover with a grain of sand held at arm's length. Some of those galaxies were shining just 300 million years after the Big Bang, far younger than anyone expected. But that was just the beginning. What JWST found next contradicted everything astronomers thought they knew. A galaxy that shouldn't exist. LAP-1b is weird, really weird, and astronomers love weird because weird usually means discovery. First, consider where it is. LAP-1b sits 800 million years after the Big Bang, roughly 13 billion light-years away. At that distance, even JWST shouldn't be able to see it. The galaxy is tiny, containing only about 2,700 solar masses of stars. That's not a typo. Our Milky Way contains over 100 billion solar masses. LAP-1b is practically invisible. So how did astronomers spot it? Gravity itself became a lens. Between us and LAP-1b sits a massive galaxy cluster called MAC SJ0416. This cluster contains trillions of solar masses of ordinary and dark matter. All that mass warps spacetime around it, bending and magnifying light from objects behind it, like a cosmic magnifying glass. LAP-1b's light got boosted by a factor of 100. Without this gravitational lensing, the galaxy would be completely undetectable, even to Webb. Think about what that means. We needed humanity's most advanced telescope, operating at the edge of physical possibility, and a trillion solar mass cosmic lens perfectly aligned between us and the target. The odds of this configuration existing are astronomical. We got lucky. But the magnification wasn't even the most shocking part. When astronomers analyzed LAP-1b's spectrum, the fingerprint of light that reveals what something is made of, they found something that made them question their instruments. The stars contained almost no metals. We're talking trace amounts, a tiny fraction of what our sun has. This isn't just unusual. In the modern universe, it's essentially impossible. Every star we've ever studied contains metals forged by previous generations of stars. LAP-1b's stars appear to have formed from pristine, untouched primordial gas that had never been processed through a stellar interior. There's more. The radiation streaming from these stars is extraordinarily hard, meaning it's packed with high-energy ultraviolet photons. Normal stars don't produce radiation this intense, neither do typical black holes. Only one type of object matches this signature: massive, metal-free population 3 stars burning hydrogen at temperatures we've never directly observed. The smoking gun. Skeptics immediately pushed back. Maybe LAP-1b's stars aren't metal-free. Maybe they're just hiding metals somewhere the spectrum can't detect. Maybe the instruments were miscalibrated. Maybe gravitational lensing distorted the data in unexpected ways. Fair questions. Science thrives on skepticism, but the evidence kept piling up, and each new finding pointed in the same direction. The carbon-to-oxygen ratio was wrong. Not just slightly off, dramatically different from any known stellar population. In the modern universe, stars produce carbon and oxygen in predictable proportions based on their internal fusion processes. LAP-1b's ratio matched theoretical predictions for primordial nucleosynthesis, the specific chemical fingerprint expected from the universe's first generation of stars. Then there's the dark matter problem, except in this case, dark matter isn't a problem, it's a solution. Observations revealed that LAP-1b's visible mass, its stars and gas, represents only a small fraction of its total mass. The rest, dark matter, lots of it. The galaxy sits embedded in a dark matter halo far more massive than its visible components suggest. Why does this matter? Because theoretical models predicted exactly this arrangement decades ago. The first stars should have formed inside small dark matter halos that acted as gravitational anchors, pulling primordial gas together until it could collapse and ignite. LAP-1b matches this prediction almost perfectly. Team leader Eli Visbal from the University of Toledo explained the significance. To discover POP3 stars, we really needed the sensitivity of JWST, and we also needed the 100 times magnification from gravitational lensing provided by a galaxy cluster between us and LAP-1b. Decades of technological development and cosmic coincidence aligned to make this single observation possible. But there was one more piece of evidence that clinched the case, something so unexpected that researchers had to triple-check their analysis. The ionizing radiation escaping from LAP-1b was extraordinarily efficient at stripping electrons from surrounding hydrogen. This escape fraction matched predictions for pristine stellar populations, but differed dramatically from what we see in metal-enriched galaxies. In other words, everything pointed in the same direction. The chemistry was right, the mass was right, the dark matter structure was right, the radiation profile was right. Either we had found population 3 stars, or something equally exotic was happening. Rewriting cosmic history, if LAP-1b truly hosts population 3 stars, the implications ripple across every branch of astrophysics. Start with reionization, the cosmic phase transition that made the universe transparent. For hundreds of millions of years after the Big Bang, neutral hydrogen fogged the cosmos. Light couldn't travel far before getting absorbed. The universe was opaque, a cosmic curtain blocking our view of the earliest epochs. Then the first stars and galaxies switched on, and their radiation began ionizing that hydrogen, stripping electrons from atoms and clearing the fog. This process, called the Epoch of Reionization, transformed the universe from opaque to transparent, allowing light to travel freely for the first time since the Big Bang's afterglow faded. Astronomers have debated for years what powered reionization: small galaxies, large ones, black holes. LAP-1b suggests the answer might be simpler than expected. If tiny galaxies packed with population 3 stars were common in the early universe, their intense ultraviolet radiation could have driven reionization from the bottom up. But here's where it gets really interesting. Population 3 stars didn't just shine. They died. And when a star 100 times more massive than our Sun dies, it doesn't go quietly. It explodes as a supernova of almost inconceivable power, seeding the universe with the first heavy elements. Every carbon atom in your body, every oxygen molecule you breathe. Every iron atom in your blood, all of it was forged inside stars that lived and died before our sun was born. But those elements had to come from somewhere. The trail of cosmic chemistry leads back to population 3 stars, the original factories that started the entire chain of element creation. LAP-1b might be showing us those factories in action, still burning with primordial fire 13 billion years ago. But wait, what if they're not stars at all? Just when the population 3 story seemed settled, another possibility emerged, one even stranger than primordial stars. In 2025, a separate team studying JWST data identified 4 extremely distant objects that didn't behave like any known stellar population. They appeared point-like, emitted radiation consistent with hot hydrogen-helium atmospheres, and showed virtually no metal signatures. Sound familiar? But these objects had one crucial difference. Their spectra showed strong singly ionized helium absorption, a feature difficult to explain with normal nuclear fusion. Some researchers proposed a radical alternative. These might be supermassive dark stars. Wait, dark stars? What does that even mean? Dark stars aren't powered by nuclear fusion. They're powered by dark matter annihilation. Here's the theory. In the early universe, dark matter was denser and clumpier than it is today. Inside those dense clumps, dark matter particles occasionally collided and annihilated each other, releasing energy. If enough dark matter concentrated in one place, that energy could heat a gas cloud from the inside, preventing it from collapsing into a normal fusion-powered star. Instead, you get something unprecedented. A star-like object potentially 1,000,000 times more massive than our sun, burning bright for millions of years, powered entirely by the invisible matter that dominates our universe. No fusion required. And when these dark stars finally exhausted their dark matter fuel and collapsed, they might have become the seeds for the supermassive black holes we see in the centers of galaxies today. This would solve one of cosmology's most persistent mysteries. How did billion solar mass black holes form when the universe was less than 1 billion years old? Normal stellar evolution can't explain it. The math doesn't work. There simply wasn't enough time for black holes to grow that large through ordinary accretion. But dark stars collapsing directly into massive black holes, that timeline fits perfectly. The implications are staggering. If dark stars existed, they would connect 2 of the biggest mysteries in modern physics: the nature of dark matter and the origin of supermassive black holes. One observation could illuminate both problems simultaneously. Are the JWST candidates dark stars? Population 3 stars? Something else entirely? The debate is just beginning. The questions that keep astronomers up at night. Let's be clear, nothing is confirmed yet. LAP-1b represents compelling evidence, not proof. The dark star candidates are intriguing, not verified. Science moves slowly for good reason. Extraordinary claims demand extraordinary evidence. So, what questions remain? First, astronomers need more examples. One metal-poor galaxy could be a statistical fluke. 10 would be a pattern. 100 would rewrite textbooks. JWST is already targeting fainter, more distant candidates that might push even closer to the cosmic dawn. Second, the dark matter connection needs testing. If LAP-1b's dark matter halo matches theoretical predictions across multiple independent measurements, that's powerful supporting evidence. If the numbers don't align, the entire population 3 interpretation might need revision. Third, and this is the big one, astronomers want to catch these stars dying. A population 3 supernova would be unlike anything we've ever observed. The explosion would be extraordinarily luminous, potentially visible across billions of light years. Detecting even one would transform theoretical models into observational science overnight. Could we see one happen in real time? Possibly. These massive stars live fast and die young. If we're watching a population 3 star right now, it might explode within decades or centuries, an eye blink in cosmic terms. The race is on. JWST's observation queue is packed with proposals targeting the earliest galaxies. Every new spectrum could reveal another LAP-1b, another dark star candidate, or something entirely unexpected. Theoretical models are being refined. New search strategies are being developed. The entire field of early universe astronomy is experiencing a renaissance. And here's the thing, we're probably missing most of them. Gravitational lensing is rare. Most population 3 galaxies don't have conveniently positioned galaxy clusters to magnify their light. The ones we're finding represent the tip of an enormous cosmic iceberg. The universe keeps surprising us. Why? This discovery changes everything. Step back for a moment and consider what we're actually talking about. We're observing light that left its source 13 billion years ago, before Earth existed, before our solar system formed, before most galaxies in the observable universe had assembled their stars. That light carries information about a time when the universe was fundamentally different, smaller, hotter, simpler. A cosmos where the periodic table hadn't yet been written, where the chemical complexity that makes life possible didn't exist anywhere. LAP, 1-b, and objects like it represent windows into that primordial era. They're not just distant galaxies, they're time machines, showing us the moment when complexity emerged from simplicity, when the first atomic forges ignited, when the universe stopped being uniform and started becoming structured. Every discovery in this field connects to fundamental questions about existence itself. How did the elements that compose your body get created? How did galaxies form? How did the supermassive black holes at the hearts of those galaxies emerge? How did the universe go from a hot soup of particles to the complex cosmic web we see today? LAP-1b touches all of these questions, and we're just getting started. JWST has only been operational for 3 years. Its instruments are performing beyond specifications. Its mirror remains pristine. Astronomers estimate another 20 years of operational life, 2 full decades of pushing deeper into cosmic history than any previous generation of scientists ever dreamed possible. What will we find? No one knows. And that's exactly what makes this so exciting. The next few years could bring confirmation or contradiction. More LAP-1b analogues might emerge, strengthening the case for population 3 detection. Or alternative explanations might surface, forcing astronomers back to the drawing board. Either outcome advances our understanding, because that's how science works. We make predictions. We build sophisticated instruments to test them. We analyze the data with ruthless honesty. And sometimes, just sometimes, the universe reveals secrets it has kept hidden for billions of years. Whether LAP-1b hosts primordial fusion-powered stars or exotic dark matter-fueled giants, the discovery represents something truly profound. Humanity's remarkable ability to reach across unimaginable distances and peer back to moments when our universe was newborn. The search continues. Fainter targets await observation. Deeper mysteries beckon exploration. And somewhere out there, in regions of space we haven't yet observed, the very first light ever emitted might still be traveling toward us, carrying stories from the dawn of time itself. What do you think about the universe's first stars? Are we finally seeing population 3 objects, or is something even stranger waiting to be discovered? Let us know your thoughts in the comments below. We'd love to hear what you think about this incredible discovery.